All right, we're ready to do our last step in solving this 3D example truss problem. In the last video, we found the displacements at node number 1. In this video, we've been asked to find the stress in each bar element. How are we going to find the stress in each bar element? The way we're going to do that is we're first going to remind ourselves of the definition of strain in a one-dimensional bar element of constant area, and then remember the relationship between strain and stress. To that end, I've drawn a diagram here of a generic bar element of constant area that exists in some generic truss. This generic bar element has a generic length L. At one end is a node numbered node I. At another end is another node, node J. Some force has been applied to this bar element, and due to that, this bar element has stretched, and node I has been displaced by some amount U I hat, and node J has been displaced by some amount U J hat. Remember, the U hat represents the displacement in the local coordinate system, where this direction is the I hat direction, and of course, this all exists in some larger global coordinate system, X, Y, and Z. All right, so if this is the amount it's stretched, the strain is defined for a one-dimensional bar element of constant area as the total amount the bar has stretched divided by the original length of the bar. If I wanted to write that out, I would say that is the amount this bar has stretched is uj, this distance plus this distance. But of course, this distance, the vector is in the opposite direction. So I'm going to subtract ui from uj. That's why I get uj hat minus ui hat. I'm going to divide that, of course, by the length. That'll give me the strain. I wasn't asked for the strain. We were asked to solve for the stress. But I can relate strain through stress by this formula, where I can say that the stress in the bar element is equal to the strain in the bar element times Young's modulus. So if I wanted to find the stress in this bar element, I'll just take this formula and multiply it by E. I'm going to rewrite this formula using vectors. I'm going to replace the uj hat minus ui hat with a row vector -1, 1, and multiply it by this column vector ui hat, uj hat. Hopefully you recognize this vector as the local stiffness, the local displacement vector in the local coordinate system. Now we just solved for the displacements in the global coordinate system. I can get this vector by replacing this vector with the local displacement vector for a particular bar element in the global coordinates times the transformation matrix. So let me take this equation and substitute it into this equation. That'll yield this equation. Since this vector is always the same and this matrix is always of the same form, I can go ahead and do this multiplication of this matrix times this vector ahead of time. What the result will be is a one-dimensional row vector, -cx, -cy, -cz, cx, cy, cz. Remember, all of these cx's, cy's, and cz's represent cosines theta x, cosine theta y, and cosine theta z, where the theta x, theta y, and theta z are the angles that relate the local coordinate system to the global coordinate system. Now, this formula, which is probably a formula you should memorize, will allow you to find the stress in each bar element just with the knowledge of the various angles that relate the local coordinate system to the global coordinate system and the global displacements for that particular bar element. This is probably also an equation you should memorize, although a particularly nice professor may include this equation on a formula sheet that you'd be allowed to use on an exam. I don't know how nice your professor is. I haven't decided how nice I am yet. So now I've just taken that last equation, I've rewritten it up here, so I have some room to apply this equation to our 3 bar elements. So let's apply this equation to bar element number 1. From the previous videos, I know this theta x, theta y, and theta z, and I know, or at least I know the cosine theta x, cosine theta y, and cosine theta z. I can plug that information into this matrix. Remember, Young's modulus was given to us, and we calculated the length of the bar element in an earlier video. I found the displacements at node 1 in the last video. The displacements at node 2 are all 0. So I'm going from bar element number 1 goes from node 1 to node 2. These are my displacements for node 1. These are my displacements for node 2. I can go ahead and carry this out. This is a simple dot product multiplied by the scalar value, and I'll find that the stress in bar element number 1 is 20.51 megapascals. Okay. Now I can use the same formula for bar element number 2 and bar element number 3. When I do that, remember I gave you a rule of thumb to follow when you calculate out these various cosines about what node you should start with and what node you should end with. If you follow that convention, then you should use the same convention. You'll always go from the lower node number to the higher node number when you decide how these vectors should be oriented. So for the stress in bar element number 2, you want to construct the local displacement vector the same way, going from node 1 on top to the displacements for node 3 on the bottom of your vector. In this particular case, we're going to end up with the same 3 values at the top because node 1 is shared between element number 1 and element number 2, and we end up with the same 3 values on the bottom of the vector because, like node 2, node number 3 is immovable. But that won't always be the case. You have to be careful about that for the particular problem that you're doing. Okay? But if I went ahead and I did all that, I'll leave doing it, the steps for doing that as a sample problem. I don't know why these should not be triples. They're not definitions. I'll end up with 4.51 megapascals, and on the third stress, I will get 5.29 megapascals. We were asked to solve for these values, so I should put a box around them if I want full credit on my homework. This ends lecture number 7. This also ends our 3D truss example problem. In the next set of videos, lecture 8, we will discuss how to use symmetry to reduce the complexity of some of these problems going forward.